Expecting temperatures in the mid to low 80s today. That's where we were on Thursday and Wednesday. Weekend.
We're in lovely Greenville, South Carolina at a supermarket that runs on CO2. This particular store has a Cascade system in it. I'll show you guys what it's all about and kind of how it works. Hey rack, this is rack 2. This is the rack that we're using to change the CO2 vapor into a CO2 liquid, and that's what we're using to circulate through the store. We have an Emerson E2E controller running all this equipment. So what we're doing here is we're using this rack to chill the CO2 to get it to a liquid state so that we can put it down in the store at a safe pressure. Big green vessel, that's what's holding all of our CO2 liquid. And then we have our condenser evaporators. We have 3 of them. 1, 2, 3. And what we do with this is as the CO2 vapor comes off the top of the vessel, it's pulled into this chiller. This side is our 449A liquid refrigerant. We have a plate-to-plate chiller system, and basically it's taking that vapor and turning it into a CO2 liquid. Once it's a liquid, we have pumps. Come over here, I'll show you. We have 2 pumps. They do not run at the same time. They only one at a time. And it's taking liquid CO2 from the bottom of the vessel to one of our pumps. We have 2 pumps, but they do not run at the same time. And it's very critical that at least one of them is running. As you can see, we have it insulated because it would sweat like hell. By the way, these are not cheap pumps. They run a good $10,000. For pumping CO2 liquid, it goes through a set of dryers. Our liquid CO2 comes out and over to our liquid header. All that piping goes downstairs into the store and circulates CO2. On the medium temp, all we have is liquid CO2 in and saturated vapor coming out. Very important that the CPC sensors inside the case are working properly because that's what's maintaining our temperature. Low side's a little bit different. To get the negative 15 degree coil temp, negative 20 sometimes on the cases, we have to use our pressure temperature chart for R744, which is CO2, to get that temperature. Just for reference, on this particular one, we're running 200 pounds of suction pressure in order to achieve a negative 15, negative 20 degree saturation inside of our cases. So in order to do that, we got to drop the pressure really low, and we're using electronic pulse valves basically in the case for a metering device going into the coil, which turns in liquid, the vapor, then the compressors, CO2 compressors, bring the vapor in, of course compress it, goes through the discharge line, through our oil separator. Discharge line goes out to a device we call a de-superheater. Basically what the de-superheater does is it's going to remove all the excess heat created by the compressors before it goes to our condenser. But I can feel that. That's a cool line. That's a hot line. So that's our discharge coming from the compressor. And this is the return going to the compressor. It's still a discharge line and it's strictly vapor. All we've done is remove the excess heat before we introduce it to our condenser evaporator inside. Now, the only thing that controls this is an outdoor air sensor. If my outdoor air sensor drops below 60 degrees, there's enough line set and enough coil room that it's going to remove the heat without the fan running. Now that we've gone through our de-superheater, we have that cool gas coming over here, and as you can see, it tees in to the top of where our vapor comes off the top of the vessel, and it goes into our chiller. Basically, side of the chiller is our CO2. This side's going to be our 449A, and these modulating valves are controlled through an XM controller inside the rack. And we're basically just modulating how much this valve opens to feed our condenser evaporator. The reason it's a condenser evaporator because it's the condenser for the CO2 compressors, and is the evaporator for our vessel to change state. These valves are controlled by the XEV superheat controller. But if we come into our E2 controller, we can see condenser 1, 2, and 3. So we can get a quick view of how everything's running. That's condenser 1, control page down, condenser 2, and you can see our suction pressure is the same on there because they do use a different transducer for each condenser evaporator. These are our main breakers for our compressors, and as you can tell, it's three-phase. This is a 208 three-phase unit. Goes down to our contactors. Those are our contactors. We have different breakers. Those are the control breakers for our contactors. So if I wanted to work on this contactor, I could turn the power off to the control breaker because they are separate. They feed from separate power. Just because you turn the breaker off, you got to kill the control breaker. Then, of course, our XEVs, we have transformers for various different things that we're running there, like all of our boards. You can see our boards down here. These are all of our safety relays. One thing we did, we came up with these sheets and we put points on there to tell you what it's doing. That way, you know, when guys are in here trying to diagnose something, they can see what's going on. Like here, we've got the upper cascade main switch, and we put notes in there. MT1 will turn off all loads. The lower cascade solenoid, overpressurized relays, CO2 pumps, upper cascade will stay energized, but the lower temp suction group will pump down. And this helps everybody out so much. And that's a basic diagram of how everything works. Oops, let me turn it the right side up for you. This is the upper cascade, this is the lower cascade. Now, with that said, with the safeties that I was talking about, if we ever have a power failure here and it's off for a long time, when the power comes back on or something fails, we have systems that try to prevent us popping off relief valves on our CO2. CO2 wants to be at a high pressure. It loves being a high pressure. So we want to do everything we can to try to keep it from doing that. I took the panel off so you guys can see it. That's our relief valves up there. Our highest one is 650 pounds. So if we get over 650 pounds on our main relief valve, we're going to pop off and start losing CO2. Well, guess what? When the power goes out, I don't have anything cooling it, so it's going to want to do that. So what they've done is they incorporated an auxiliary unit for the control our CO2 vessel to keep the pressure low so we don't lose any CO2. Now, the auxiliary condenser is doing the same thing that rack's doing, just at a very smaller scale. It's just pulling vapor, high pressure vapor off the top of the vessel, cooling it down and putting it back into the vessel so we can maintain our pressure under 500 pounds. So when we're doing a general maintenance in the store, we always come make sure that that thing's working because we don't want it to fail. Let's go outside and I'll show you. So this is our auxiliary condenser. And as you can see, it's just a basic refrigeration condenser with a scroll compressor. So when that liquid line solenoid inside energizes, it's going to create higher pressure, bring the low pressure switch to close, and bring the compressor contactor on. It's going to start cooling that CO2 down for us. Like I said, this is small scale. All it's supposed to do is keep the CO2 from exceeding 650 pounds. We try to keep it around 500 pounds. Now, with that being said, if something fails in the rack, we have something called a critical alarm that's going to shut all of our cases down. This is our alarm panel. We're going to use a scenario, say the power's been out for 4 hours. All that CO2 is warm, we need to bring it back up. The rack's going to come back on. The first thing that's going to happen is we're going to de-energize a bunch of relays. These are known as our overpressure relays. After that 15 minutes, our first timer is going to energize. This is going to bring on our first set of relays because we don't want to bring them all at once. If I try to bring all that heat back up here at once, those compressors aren't going to be able to handle it. It's going to shut off on a high pressure. We're going to hit over 500 pounds. Time delays are set up 15 minutes apart. We're starting to cool some of the cases down, bring some heat up. Our pressures are rising, and then they're dropping again. Gives it enough time. Hey, we can energize our next set of relays. The next set of relays energized, and then we bring those cases down to temp. The next set of energizers, so on and so forth until I'll come back on. Anything made by man is subject to fail. I have had these relays not energized before. And so we keep spare relays on site when it doesn't happen. Now, there's a lot of safeties when it comes to CO2, because like I said, it wants to be at a high pressure. And we have to put a lot of engineering into it to keep it at a lower pressure. CO2 is the way to go. We have like a global potential warming of 1, a GWP of 1. It's the lowest. All other refrigerants are based off CO2. In a couple of weeks, I get to go to a transcritical store and start it up, and we can talk about that at a later date. I haven't experienced one of those. There's a lot of guys out there that have, and they love them. You just got to get used to it. You're dealing with, 1,000 pounds, 1,200 pounds of pressure. Let me walk you through the operation of this 449A parallel rack. Of course, we have our compressors, right? We have 5 compressors. This is our discharge line, a discharge leg. We're leaving the compressor in a high pressure, high temperature state. So as that refrigerant is leaving the compressors, it's taking some oil with it. We want that oil to get back to the compressors, and that's what our oil separator does. This particular one is a coalescent filtered style. It has a coalescent filter. It squeezes the oil out of the refrigerant, and then it's going to drop that oil at the very bottom to our oil flow. And it's going to push all that oil that it caught back up through this line and into our oil reservoir. And as you can see, the oil's coming up through here. Once it's in our oil reservoir, it's going to come down to an oil filter, go back over, and it's going to feed it back into our compressors through our oil pipe. We have discharge gas. We have some reclaim tanks, so we're going to use that extra heat to heat the hot water. It's free heat, right? We want to do that. Once it's gone through our heat reclaim, it's going to go to our piping and our outside condensers. And then these are our condensers for that Rack 2 449A. There are not any CO2 condensers out here. Remember earlier I was talking about the de-superheater. It's not really a condenser. A condenser is what it says it is. It condenses from a vapor to a liquid state. The de-superheater just removes extra heat. It doesn't change state. The condensers is what changes the state of the refrigerant. So we have high discharge, high temperature gas going into our condensers and coming out a high pressure liquid. Liquid coming out of the condensers is always going to be whatever your ambient condition is. So if I have 67 degree outside temperature, I'm probably going to have 67 degree liquid if I have enough refrigerant in there. If you don't have enough refrigerant in there and you're coming out flashing, all bets are off. And same goes for an outside temperature of 95 degrees. I can only cool the liquid. I can change state. I've got it changed state, but it's only going to get as cold as its outside condition. There's a lot of heat. You wouldn't think it, but I mean, look at there's 2 stacks of condensers feeding that one rack. That's a lot of gas. That's a lot of heat. We're sending a 0 to 10 volt DC signal to these motors, and it's coming on and on as needed. It's the higher the voltage, the faster it runs. Now they do have the technology now, and I think these have it. I'm not sure if I've set them up that way, where you can go 0 to 10 volts, and 0 volts being 100% and 10 volts being 5%. And they do that for a fail-safe reason. So if I lose a board in this rack in the middle of the night, these condensers will go to 100%, and I'll end up just having a really low head pressure that I'll have to fix. But I'm not tripping out on high head, which helps the compressors, helps it short cycling. They're efficient motors, they're good motors. Like I said earlier, everything made by man is subject to fail, so they do need replacing every now and then. Okay, as I was saying before about heat reclaim, as you can see all this tricky piping, we have a heat exchanger right here. And basically what happens here is we have discharge gas coming off the compressors going into this heat exchanger. One side's refrigerant, the other side's glycol, and we're warming up that glycol. And as we're warming up the glycol, we have a pump that we're pumping glycol. It's hot glycol, probably 145, 120 degrees, depending on the conditions. That warm glycol is being pumped and circulated through a coil out in the main AC. Once again, that's free heat. Why not take the heat of the compressors? If I got to have the heat in the stores, let's just dump the heat back into the store. We're going to use a pump that pulls about 3 amps. So on these compressors, of course, we're going to have a lot of safeties. This is going to be our high pressure safety. This one's set for 345. It's contested. So when the pressure gets above 345 pounds, it's going to open up the control circuit going to the contactor and shutting it off. We also have our sensor for oil, so it's sensing oil pressure. And if we lose oil pressure, we're going to turn the compressor off because we want to save it. We also have a low pressure switch. If we get too low of a pressure, we don't want to pull in a vacuum, so we're going to shut the compressor off. This is our oil pot, oil regulator as some call it. It's basically a floated system, so as oil drains out of the compressor, that float's going to open up a port and allow pressure. As long as I have the correct pressure here, it'll put more oil back into our oil pot. This is just the electrical cover for the compressor. That's where all of our safeties. Inside there, I'm not going to take it apart, but we do have a current relay in there that kind of senses if that thing's pulling the right amount of amps, and it'll shut off if it overheats. This is our oil pump. So this is connected to a shaft that is connected to the cylinders, all the way connected to the motor. And as it turns, it pumps oil through holes in there and keeps all of our pistons lubricated. We also have a crankcase heater. So when the compressor is in this off mode, it keeps the bottom of that warm to keep any refrigerant in there from condensing to a liquid. And once you turn it on, if it's in a liquid state, it's going to bang like hell, because why? You can't compress a liquid. So that heater keeps that bay warm in order to keep it in a vapor state. On these compressors, we have what we call unloaders. Basically what this does is it shuts off this bank. So when this energizes, this will become a floating head. And all it is, the cylinder's still running, but it's doing no work. Those valves open up and it just sits there and allows that to work. And you can actually see it on an amp meter. We'll probably pull 30 amps when we're fully loaded, and we'll probably pull about 15 to 18 amps when it goes unloaded. Unloaded means that's energized, that side's off, and we're just pumping that side. This one, if you notice, has two. Now the reason they use unloaders, I'll show you here, is the stages on our compressors. So if we go to our suction setup, you can see our stages. We have a digital compressor 1, compressor 2, unloader for stage 3, compressor stage 4, stage 5, and stage 6. Some guys get confused when they see this because they're not paying attention that it's stages, it's not compressors. We have 5 compressors, we have 6 stages. With the digital unloader, this compressor will remain on all the time. And all we're doing is energizing this, or energizing this, or both at the same time. If both of those are energized at the same time, that compressor is doing no work. But the contactor stays energized, the pistons stay running, and I don't have that high load amp every time I turn a compressor back on. We've left the condenser, we're coming back into the motor room as a liquid state. Here's our liquid lines coming from the condensers. We have check valves. The reason we have check valves, 2 check valves, is because when we have a low ambient condition, we're splitting the condenser in half, and we're going to pump the other half out. So when we're pumping it out, we don't want that liquid to go back out into the condenser. We want to keep it in the system. So we split it during low ambient conditions. We get below 50 degrees, it's going to energize the solenoid to go ambient conditions. We'll go back in the front, and you can see where it enters the receiver. And here it is, the inlet of the receiver. You see the blue valve back there? That's a holdback valve. That's what we call it, the A8 valve. All it's going to do is during low ambient conditions, it's going to hold pressure back on the condenser because we want to keep our head pressure up. If we get too low of a head pressure, none of the system will work. So during low ambient conditions, that thing doesn't energize, but it's got a pressure regulator in there that forces it closed off a little bit. During normal conditions, 100% liquids coming into our receiver. That's what this big tank is. It's got an indicator to tell us how much liquid's in there. Not very big one comparatively speaking. There's no way I could pump this whole system down into that because of the size of the condensers that are out there. But that's basically what it is. It holds our extra liquid. Anyway, we're coming out of our receiver of liquid. Of course, we got some dryers because we're going to clean it up a little bit. And then it comes out of our dryers, and there's our liquid header right there. That's what's feeding our evaporator condensers. As you can see, we have a long pipe. This is nothing but solid liquid, or at least it's supposed to be if it's got the proper charge into it. We have a ball valve if we need to isolate it for whatever reason. It comes over, and it comes to our upper Cascade solenoid. If this is not energized, nothing works. This one thing has to be energized for the system to work. If it's not energized, we are not feeding liquid to our condenser evaporator, which is right here. So we go in as a liquid, we've condensed our CO2, and now we're in an evaporated vapor state coming out. Now this is our suction line, suction header. It's insulated because it gets cold. You can see it'll sweat a little bit. We have 3 condenser evaporators, so we have 3 headers coming into it. This is our suction vapor coming out. It's piped into here, comes over here, comes into our suction header. A lot of piping, isn't it, guys? And it comes to this big vessel. Now that's an accumulator. You don't want to confuse it with a receiver or a holding tank or anything. All it does is, hey, maybe I had some liquid coming back and I didn't boil everything off in my chillers. If I didn't boil anything off and I got a little bit of liquid come back, this will drop in there, help the evaporator, and just pull straight suction to protect our compressor. Now we got vapor coming back in, and we start the process all over again. The compressor compresses, becomes a high discharge, sends it out to the condenser, and it just circulates over and over again. So this part goes piped downstairs to our water chiller in the bakery, and it's the only thing that's 449A that's in the store. Everything else is CO2. So that's a basic rundown of our CO2 Cascade system. I know there's probably a lot of questions. I'd love to try to answer them best I can. You know, I love refrigeration. I love supermarkets. I love this new technology. I want to try to spark an interest in other people and bring them into the field, because man, this is some cool shit we get to work on. Not everybody gets to work on equipment like this, and to have that knowledge and that experience is going to improve everything from how you think and how you react and what you're doing in life. And I try to teach my guys how these things work and to do a good quality maintenance, because if you don't schedule a maintenance for your equipment's going to schedule it for you. So that's a wrap, guys. I hope you enjoyed this segment of it. Hopefully there's more to come. We'll get into other stuff. We have some glycol systems I'd like to get into, conventional rack systems. You know, if you guys want to put some comments in, tell me what you think, questions that you might have, please do so, and let me know, and I'll be sure to read all your comments. Y'all have a great day. Bye.